All right, we're going to get started. If everyone could take your seats. Real quick, we'll do the survey winner for yesterday. I am actually very impressed. We had almost 200 survey responses, which means that this is finally working. Thankfully, most of them were pretty complimentary. Is Mark Antone in the room? Mark Antone? No? Oh, that's a shame. No iPad mini for him. How about Hans Edelman? There we go. Hans, your prize is with the registration desk. You're welcome to grab it now or later on if you'd like. So we still have 2 more of these to give away. We'll give away one for the survey responses for today, and we'll give away one for the survey responses for Wednesday. So please, after you've seen the content, fill them out. One other thing to keep in mind is that if you want to fill them out as the presentations happen, you can do that. You can go in and edit your responses later. So feel free to fill it out for this one and then fill it out for the next one and come back later on tonight if you'd like to give us a more complete view of what you saw for the rest of the day, including the tracks. One other interesting programming note: for the first time ever, I'm extremely proud to announce that all of the content from yesterday, all of the recorded content from yesterday, is now live on YouTube. So you can actually pull up all of the sessions now if you'd like to send them to your friends. It's fantastic. We've, over the years gotten requests to get this stuff up quicker than, a week or 2 weeks after, and so we're extremely proud. I'm not sure if it's linked, each one is individually linked to the agenda yet. If it's not, it will be by the end of the day, but it's certainly all searchable on YouTube by just searching for NANOG 59. With that, I'd like to invite David Swafford up to talk about data center networking at Facebook. Thank you.
Thank you. Hi, I'm David, and today we're going to take a look at data center networking over at Facebook. Before we get started, though, I want to give you a few key stats to give you some context of what we're dealing with. We have a lot of people on Facebook today, specifically 1.15 billion people active every single month. They upload 350 million photos every single day. That alone accounts for 7 petabytes of storage consumed each month. In terms of the network graphs that we see as on the engineering side, this graph right here is actually showing about a year's time span, comparing traffic in and out of Facebook as a whole, to and from the internet, which is shown in green at the bottom, labeled machine to user, versus our traffic on the inside of the network, the machine to machine traffic. The time span of this graph here is about a year's span. So as you can see here, over just 1 year, we've literally doubled, if not almost tripled, the traffic on the inside of the network, while remaining relatively stable in the traffic leaving and entering our network. This is just mostly due to the dynamic nature of our application and things becoming more and more involved, or more and more media rich. For example, high-res photos in your newsfeed and just more content being produced on the inside. So we're going to be talking throughout this talk about clusters at Facebook. So to give you some idea, a cluster in our world is just a unit of computing power. It's a bunch of servers, a bunch of racks, and related network gear. So taking a look at what it looks like when you actually hit facebook.com, from a web browser or phone, you initially hit a web machine in one of our front-end clusters. That web machine, though, doesn't have all the content you actually need. It's just going to have the static content. So your request is going to generate hundreds, if not thousands of requests in the background to all of the different machines that feed things like newsfeed, advertising, even the messages and photos. And then ultimately you have database servers in the back end. One key challenge we have at Facebook is that a single user's request to one web machine in the front end easily generates hundreds, if not thousands of requests in the background, which is kind of what we saw on that graph earlier. So microbursting, for example, is one definite problem we see on a day-to-day basis. Looking at what our network looks like, though, that used to power these clusters. So we're going to walk through different generations throughout this talk. So our first generation cluster here, it was entirely a layer 2 domain. We had a rack switch at the top of every rack. A single rack switch, though, and still today a single rack switch, because we don't trust any single rack. But we had a rack switch at the top of the rack. It was purely a layer 2 environment, though, That rack switch had an IP address for management. It did layer 2 switching and nothing else, though. It connected upstream to a pair of cluster switches, which are kind of along the lines of what you might expect in a data center environment, large chassis-based platforms that stood pretty high off the ground from one of a few vendors. Now, the early designs of this used 1 gig and then eventually used early first-gen 10 gig. Looking at some challenges, though, that we had with this design, one of the big ones was usable capacity. We only had 2 cluster switches. So regardless of redundancy in a box, we always plan for an entire box going crazy. So that means right away, we have to over-provision 50% in this model. But as we started to adopt 10 gig, it wasn't really 10 gig at that point. It was oversubscribed 10 gig. So usable capacity was even far less than what it looked like. But ultimately, why we left this design was really the layer 2 scaling challenges that we ran into. So as we grew these clusters bigger and bigger, we didn't exceed any manufacturer spec in terms of how many MAC addresses we could throw at these devices. But what we found was they started to choke. Literally, things like MAC learning became problematic. Our processing was something completely unheard of to a device, and it would just fail over, or completely fall over. So, and that wasn't any specific vendor or platform. It was just one of the things we noticed as we grew. So looking at our second generation cluster, we had a lot of layer 2 challenges. So we said, let's go ahead and keep layer 2 constrained within the rack. So now we still have a bunch of servers with a rack switch at the top. Now that rack switch is a router to our environment. It runs a routing protocol upstream to our cluster switches. In this design, we also added 2 more cluster switches. So that way, when we lose one, we only have to over-provision for 25% of a failure. And in this model, we actually have line rate 10 gig. So we legitimately have 30 gigs out of this rack, which is great because now the application is no longer suffering from fighting to, or starving to get some bandwidth. So I mentioned we run a routing protocol to the rack. Specifically, we run BGP as the only routing protocol to the rack. You might ask yourself why. So a few things that we really like about running BGP within the data center is it provides a lot of granularity for control. We use BGP communities to tag routes at different locations so that we can finally filter on them without having to do exact prefix matching. We can also do control inbound and outbound in multiple layers to kind of protect ourselves. Also, it scales really well. For example, it runs the internet, much larger than us. So that kind of gave us some confidence going into this. So looking at one of the challenges we led into from this is that as we grew, in the graph we saw at the beginning of the slides, our traffic between clusters is pretty heavy. And so while we have a lot of traffic growing going in and out of the internet, the traffic between clusters was growing at such an exponential rate that it became pretty hard for us to keep up. Things like backbone links were starting to become saturated. Because in the early design, we may have only had a few clusters, and they connected upstream to a backbone. And as we grew, they all still connected upstream to the backbone, regardless of their location. But before we go into this problem a little bit more detailed, let's talk about why we have a backbone. So our purpose is just to connect our data centers together, and also to connect our private and transit peering. So one of the problems we started running into, though, is that the backbone devices that were connecting these clusters, they're very powerful. They are high-end devices that can carry easily millions of routes. But their density in terms of ports, like for 10 gig, is much lower than on the data center side when you look at it by the actual cost per port. So they became almost too powerful for the needs of tons of traffic between the clusters within the data center. So we stepped back, and we said, you know, there's just got to be a better way to kind of approach this. So that led to the next drawing here. Within each data center region, we built a separate back-end data center network. So by data center region, we have, for example, the West Coast of the United States, the East Coast. And each of these will have one or multiple buildings in a little campus. So what we do in this design is that we cross-connect all of the clusters in a full mesh to this back-end data center network that's local to that little data center region or campus. And now the only traffic actually hitting the backbone is traffic leaving that data center or going in and out to internet peering providers. So that worked for quite a while. It gave our application owners a lot of room to grow and start turning on more and more features that just needed a lot more bandwidth. But it's not perfect because there's still reasons to always improve on everything. Specifically in our environment, one of the big challenges we saw with this design is that we had a lot of chassis devices throughout the environment. And chassis devices are pretty complicated. They're typically proprietary, and they also have lots of state to maintain, lots of line cards, lots of chips and ASICs. That's a lot of things to make sure that are actually working properly from an individual box's perspective. And as we started to grow, we noticed that they break in really obscure ways. So a great failure for us is a line card just like completely failing and powering off. But a bad failure is one where it silently fails. It still looks like it's OK, but it starts black holing traffic. And also, efficiency is another reason we want to kind of work on, because the model I just showed, we were building a cluster for photos, a cluster for web. Regardless of how much servers went into that cluster, or how many servers went into that cluster, we still needed to provide at least 4 cluster switches in the first design, or the one right before. And so there's still some minimum amount of sizing and planning to install all this. But what happens when you want to build a web cluster that's small and a photos cluster that's twice the size? Well, eventually you run out of ports, and you just build 2 of those. But your web cluster is under-provisioned, and while you can buy less line cards, it's not as easy to grow incrementally. So the third generation design that we have in place, this is a folded Clo-based data center-wide fabric. So in this model, we start out still with a rack switch at the top of every rack. But now it connects upstream to one of a handful of fabric switches. In this model 8, it could be 16, though. Right away, though, this is not really that much different. But we renamed this to a pod. So this pod is now a chunk of a cluster. Think a 5th or a 10th. And it connects upstream to a spine layer. Pretty common at first. And the idea here, though, is as we go into this design, we're trying to get away from chassis, go to smaller, more fixed platform devices that are kind of easier to manage and easier to automate. So in this model, we want to be able to grow horizontally a little bit faster. So with the click of a button, we double the spine right here. But right now, we don't have that much more capacity because it's a server pod that's a chunk of a cluster. We still need to build many clusters. So the idea is that we'll start growing these pods and eventually turn this into what's called the plane layer. So as we go to scale the entire data center, we'll have a whole bunch of pods. And they'll connect to a bunch of spines. And the spines will all basically kind of stack 3-dimensionally until you have enough ports to connect everything. The interesting change with this design, though, is that there's no chassis involved here, or maybe very small chassis in some places. It's just a lot more devices. So now instead of planning for 25% over-provisioning to lose a cluster switch, it might be over-provisioning a 16th, a 32nd, maybe a 64th of the capacity because your device maybe only has like 64 links on it instead of hundreds. This is an exciting design and also a very scary one at some point because it's very different from all the tooling we had in place. So that meant all of our tooling no longer worked, which is exciting though because it gave us the opportunity to start fresh, approach it with a brand new perspective. What software did we want that we didn't have before? What kind of analytics were we not doing? Because there's a lot more links here. There's a lot more problems for failure, or potentials. So that goes into our next section. How do we manage all of these devices? So at Facebook, we try to approach everything from a software mindset on the networking world. From configuring devices, alerting on issues, auditing and then alerting on issues, and even remediating of issues, we try to make software do this as much as possible so that we can free up our engineers to make a greater impact. Ditch the whole traditional knock perspective and have real engineers actually respond to real alarms. So for example, this frees up our team to spend time learning how to write better software, spend time to automate anything that's still done manually, and then finish this feedback loop to share back with the team so that we don't make the same mistake twice, so that we continually grow on top of each other. This is actually my favorite part about working at Facebook, because you could come in as a network engineer, have no programming or scripting knowledge, and be encouraged to grow and learn it, and then be supported to actually focus and attack a problem you see that management might not see. And it's a very supportive and encouraging environment between the whole team. So let's take a look at this in like some real detail, because what I said sounds cool and all, but let's see it actually exist. So how do we deploy a cluster switch in either the fabric model or the original models? So everything from planning the port map, generating the configuration, applying that configuration, even validating that that configuration works. For example, did those BGP sessions that you configured in your template actually come up? That's entirely done by software. We use engineers just to physically install devices and enable them for live traffic. Though the last one, we can easily automate when we feel comfortable. It's just a matter of comfort level. So let's take a look, kind of stepping away, into another system we have at Facebook. It's called FBAR, or Facebook's Auto Remediation System. FBAR creates alerts, engineers create alerts, so network engineers create alerts based on issues that they've seen. For example, a common alert might be this interface has received power on an optical link that is worse than this such and such threshold. So the engineers create these audits. And they also create remediation scripts. For example, tell FBAR what to do when it sees this alert from some device. Audits trigger alarms in our environment. And then FBAR reacts to these alarms. Looking at a real example of FBAR in use, we connect with a lot of peering providers. Many in this room, for example, at internet exchange points. So with an internet exchange connection, you have a lot of BGP sessions involved. It's common for one of those to go down every now and then. For example, we might be doing maintenance. Somebody else might be doing maintenance. Or it might be a hardware failure. So that session normally goes down and typically involves somebody to look at it. So instead, we use software to kind of help filter this and kind of analyze the situation first through FBAR. So in this example, we're on a router that dropped its BGP session at an internet exchange. That device generates a syslog message about the session going down. That creates an alarm. But that alarm doesn't go to anyone right away. It goes to FBAR. FBAR says, you know, I know what that device is. It's a router and an exchange point. I know what a BGP session is, and I know what that alert means. And actually, somebody has told me what to do in this case. So FBAR will actually log in to the device and say, hey, device, I saw that this session went down. Are you still down? The device will respond back, no, it's good. But then FBAR is like, well, let's check a few things first. So FBAR will take a look and say, what interface connects to that peer? How are my interface stats looking? Do I have any errors? Do I have good light from the optical link? The device will respond back, no, everything's cool. So FBAR also keeps track of when it last saw this alarm. So assuming everything was cool, the BGP session's back up. And there has been no recent occurrence of this, it's probably safe to ignore this alarm. And in this case, FBAR will. It'll throw it away. But let's say when we went and checked with the device and saw that we had bad light levels on that interface, but the session came back up. Well, bad light levels, from our experience, is enough at a certain threshold will cause CRC errors. It'll also cause things to just bounce and traffic to get garbled. So that's likely the cause, in this case, of why the session dropped. FBAR has the intelligence there to say, OK, somebody needs to go look at this. Even though it's back up, there's a problem. And it will escalate it to an engineer. The cool part about this is it lets you eliminate the knock. Your engineers that are, like, for example, our network operations team, we don't have scripts that they read. It's not a big projection screen of watching monitors and reacting. They get alarms and tickets that are legitimately filtered already. So instead of having to filter the noise and say what actually happened, what caused this, they'll get a ticket that says, FBAR saw this BGP session drop, the interface has bad light. And now you eliminate a whole bunch of troubleshooting. So let's take a look at another section. I mentioned we have a lot of chassis at Facebook and a lot of line cards. So this drawing here is just a generic representation of a line card on a network device. Line cards by themselves, not horribly complicated in this drawing. So we've got a switch ASIC. We've got a control plane CPU. We've also got 5 controllers, interfaces, and a fabric interconnect. But it starts getting more complicated as you look at what the card actually can do. So the switch ASIC, for example, it has layer 3 tables, layer 2 tables. It probably has a bunch of other stuff, too, that it's keeping track of. So when you look at this in the form of a chassis, you have a lot of these cards connected together. So what happens when one line card goes crazy, but doesn't completely fail? And so the control plane doesn't notice it. Your route processor or your supervisor says, well, I don't see any problem. Everything's cool. You're continually flowing traffic still through these cards. But one of the cards has just lost its mind, and it starts throwing away traffic for maybe one prefix, but everything else is cool. Something's obviously wrong. But in some cases, you might not notice it until somebody reports a problem. For example, maybe your load balancer went down, and you notice it from a load balancer alarm. So in our environment, we see these kinds of issues often enough that it's kind of gotten us interested in this fabric design that we went to. And so basically the point of this, though, is you get to the point where you have enough oddball issues that you just can't trust the box. You can't trust the line card anymore. And that goes into kind of our next section. We try to monitor everything. So every link, every interface, every BGP session. We also try to monitor every fib across the entire environment. So for example, the line cards I just showed, across every cluster switch, every device with line cards, we'll monitor to make sure that the routing table in the control plane is actually in sync with the routing table on the line cards. And we'll automate that in the background to proactively check issues that I was kind of mentioning earlier. We also look at, in aggregate, tons of data from all of our servers, because they're everywhere, and they're ultimately going to see issues more likely than we might from the network device. So for example, tracking your TCP retransmit stats at the server is an interesting metric to see, because if you start seeing one section of the network doing tons and tons of retransmits, well, something upstream is wrong, because that shouldn't be normal. And that's kind of an interesting way to look at it. So at Facebook, we are a very big on this culture of automation. We try to filter all of the noise in software. We try to automate anything that's repetitive, mainly so that engineers can focus on real problems. And you might be thinking to yourself, well, that works great. You probably have hundreds of engineers doing this. In reality, we don't. We have a very small team. And it's just keeping focused and try to automate anything that you're doing today in just little chunks, stepping into bigger chunks. And it eventually builds on itself so that eventually you're doing something completely new tomorrow, new and exciting, and working on helping others kind of grow. So let's talk about our rack switches, though. So we have a lot of rack switches at Facebook, and we used to have this interesting problem. It was an install and forget model. So as we installed rack switches, whatever configuration standard was present at that point, well, that's the standard that rack switch was configured with. So over time, we had some drift, and we got to the point where the drift was pretty bad. And when we started trying to turn on IPv6, it was not a fun experience, because you had IPv6 support in new racks, but not in the old racks. But as an application, such as messaging, that wanted to use v6, well, it didn't make sense, because they don't want to turn on v6 for one data center, not the other. So it kind of stalled the progress. So specifically, IPv6 is something we're excited about. We want every part of the environment to have IPv6. And we literally mean IPv6 everywhere for real, not just at the edge. We want every single rack across every single data center to have v6. Every single service in every data center serving production traffic on v6, literally in the early part of next year. And the every rack part is actually this year. So a few things might strike your mind. Why would we want to do this? Well, in our environment, IPv4 is not going to last forever, both the amount of address space in the private range, but just as a protocol. We don't want to kind of drag on. We want to help proceed into adopting v6. Also, when you're troubleshooting issues, Band-Aids are not much fun to troubleshoot. While we don't really do tons of NAT inside, they kind of make things harder at some points. And finally, it's just really, really cool. You can put Facebook and every single IP address on every single server if you wanted to, which we're trying to do. So let's take a look at how we went about rolling out IPv6. So it involves dual stacking backbone and cluster switches. It also involves rack switch upgrades, because all of those old rack switches had to be upgraded for new code. They had to have a fresh configuration applied. We also had to turn up IPv6 for all of our services. So any code specified v4 had to be migrated to support v4 and v6. So let's look at the old way we would upgrade a cluster of rack switches specifically. So when we wanted to try out new code or new configuration ideas, we don't really have a big lab. So we typically tried out things in the web clusters. So when we wanted to roll new code, for example, to try out a new feature, we would coordinate an outage window with all of the affected service owners. We would drain traffic, meaning that we would start redirecting traffic away and from that cluster and into other clusters, which for a web cluster was easy, because there's not really any state there other than the existing active TCP connections. So once those rolled off and you stopped sending new connections, there was nothing there. And then we ultimately did the upgrades. But even in the old model, we did a lot of the upgrade work by hand. So we would have scripts that we'd run to do the reboots of like rack switches, but we would still heavily involve typing of commands to just push all this and stage all the config and code. So looking at the way we did the web cluster upgrades, let's take a look at what kind of difficulties we ran into as we tried to upgrade the other clusters. So we actually found that database clusters are pretty easy to upgrade in our environment, even though they're pretty dangerous, because if you do your cluster that happens to be the master database region for everybody, Well, you got a lot of risk involved there because you're going to be failing over database servers and trying to make sure that it's as transparent as possible. But specifically in the database realm of our world, we only have a few teams to manage. Specifically, about 5 total like on-call people or teams to work with, such as database engineers and also things like backup engineers. The web cluster was easy, I mentioned. Database cluster was surprisingly actually relatively easy. Now, looking at where we found the most difficulty, these service clusters, where all the things like newsfeed sat, the photos machines, even the advertising machines, they typically had a lot of different people involved in the same clusters. Specifically, on average, we saw about 120 unique people that we had to coordinate from the network team when we wanted to do an outage to drain this entire service cluster. One of the big problems, though, that caused some heartache there is that in our world, we have this idea of dedicated and shared racks. A dedicated rack is where one service owner owns the entire rack. So all the servers present are for photos, for example, or handle chat. But then we also have shared racks, where somebody like myself, who might need a few servers, can just go allocate them. And I would share a rack with somebody else that might have advertising machines or newsfeed machines present. So the problem that we ran into that really kind of made us step back and revisit this idea of draining the whole cluster is it doesn't make sense to make 120 people agree when one person might own 5 servers and one might own a bunch of servers. So we said, why are we draining the entire cluster? Why does it even need to be a single window? And why does NetEng have to be so heavily involved? Literally upgrading a rack switch with new code or new configuration can be automated pretty easily. It was all the extra pieces involving project managers, involving people to say, yes, you can go reboot my rack switch because it's cool now. That was the painful part. So let's take a look at an early attempt to try to solve it, an early attempt where we tried to solve this problem. We said, we're going to blacklist all the unsafe racks based on the host names present. So in our environment, a host name for a server easily maps back to a service. For example, if it handles newsfeed, it probably has the word newsfeed in it. So we went to all these service owners, specifically for one of the clusters we were trying, and said, hey, we want to go upgrade all these racks. Can't tell you when because we're too far out, but whenever. Are you safe with us rebooting your rack at any point and us not telling you? A lot of them said, you're crazy, because they want to know when we're going to reboot their rack switch. Because if their on-call gets paged for chat being down, they kind of want to know that we caused it, for example. So we spent a lot of time trying this idea, basically found that we could, and basically the model was we were going to go walk all the racks and upgrade whatever passed and did not have blacklisted hosts. It ended up being a lot of time involved asking people about this. And we didn't really get to upgrade very many rack switches at all. We still tried it, and it was a good learning experience. So looking at how we solved the problem, we said, let's split this apart. A dedicated rack and a shared rack are actually 2 completely different things, even though it's the same cluster. So for dedicated racks, meaning just photos machines are present, for example, we said, let's shift the responsibility of upgrading the rack switch to the service owner. Have them help us do the rack switch upgrade. And for shared racks, we said, we can't make everybody agree on a single window, so we're going to pick 4 of them. But we're going to pick a little bit more accurately this time. We scheduled every single rack, giving it a time slot. You're starting to be upgraded at this time and ending at this time, and built full automation around this. So for dedicated racks, I mentioned we shifted the responsibility to the service owner. You might ask yourself, you must be crazy, because what service owner wants to log into a rack switch, do their own upgrades when all they know is PHP? So realistically, though, what we found, and I'm going to talk in a minute, but we didn't actually make them log into the rack switch. But real world, we found it was a lot less time involved for all of the service owners and ourselves. No longer are we spending this time saying, hey, can we do this maintenance? Or, hey, we want to do it now at this time. Are you cool? Now it's, we need your help. You want to deploy IPv6. We want to deploy IPv6. Help us do it by launching this tool. And here's where you can go for help. And let us know if you need anything. It was pretty cool, though, because service owners actually took really quickly to this idea because it empowered them. It let them do their upgrades around their own maintenance schedules, not around arbitrary times we picked. So now they're not the user in the rack, they're the customer. And we're actually friends and actually talking and not having this tension that we had before. So specifically for the dedicated racks, where we asked them to help us, we focused from the beginning to make this a smooth user experience. So we provided software that we built So basically a CLI tool, for example, that allowed them to do a single button upgrade. They didn't have to know anything about the rack switch they were in. They didn't have to know even the name of the rack switch of their racks. All they had to do is say, I'm in this rack, and based on the standard name scheme. Do I even need an upgrade? And the tool will tell them, yes, you do. And then they can say, well, OK, cool, go upgrade it. The tool will go do the upgrade and give them some progress along the way and let them kind of view what's going on. We also focus early on to provide detailed reporting from the start. So if something goes wrong, the Service Center knows exactly what happened, and so do our engineers who need to help and resolve this quickly. And we also wanted to make it easy to manage a job. For example, if they started it and needed to stop it suddenly, that needed to be built in right away. So that way we don't start upgrading racks by accident. So I mentioned this idea of scheduling shared racks. So the reason we wanted to schedule the shared racks is we needed to provide all of the service owners accurate timing and notification. So while you can schedule something easily with like cron, for example, that doesn't really help the whole feedback loop of letting people know what's going on. So we built this system that wrapped around the timing with our task management system. So that way, when we scheduled, we sent them a task and said, hey, you're scheduled for this time slot, say 5:30 tomorrow in the afternoon or evening. And your rack is going to be upgraded between 5:30 and 6. But then the tooling we built also went and reminded them and said, hey, we sent you the, say for example, we sent the task 2 weeks ahead. Well, we'll remind you a day ahead. Say, hey, just reminder, we're still upgrading your rack tomorrow. But then, again, we'll say, hey, we're upgrading your rack right now, just in case you forgot. And so we built software to do that, specifically because a lot of services still needed to be manually drained. So we have a lot of services I mentioned earlier, the big names like photos machines, chat machines. But we have a lot of internal services. For example, servers I might manage, or servers that our monitoring teams might manage. So those might not have quite the intelligence to automatically fail over, so they might have to kind of prepare for this event. And we also said in our discussions, why not finish all of the workflow of scheduling everything and eliminate all of the pieces that typically stopped us before? So I just wanted to kind of say, or take a look at this. Where are we now? So right now, service centers handle rack switch upgrades. They literally are upgrading racks whenever we need them to be. And we've reached this point where the network is constantly upgrading itself. So you might ask, how did you do all this? Because there's a lot of pieces kind of left out. So we built a system called aggiornamento, to refresh in Italian, just to kind of do a little playful pun with everybody. And so it's a client-server model based on Thrift. It runs on Linux. It's written entirely in Python, and it's backed by MySQL. The idea of this system is to integrate every piece that was manual before. So for example, I mentioned identifying this. I mentioned there's a lot of service owners present. Well, some service owners live in one cluster but not the other. So we had to automate the step of finding out who actually lives in what cluster, and finding out who's actually on call at this time so that we're not bugging the wrong person. Also, scheduling and generating the logic to actually run and execute these upgrades based on the schedule, but also keeping it super safe. So that way, if we get off in the schedule, we don't start taking down a bunch of rack switches that we forgot to do or missed. And finally, we made job management super simple. And so I just want to ask everybody a question here. What would you do if you were not afraid? I would say automate your day job. So that way, you can focus on the impossible. I'd like to thank everybody for attending and open up the floor to questions. And on top of the questions, I actually have several teammates here, and we're going to be outside right afterwards with like a discussion area in case anybody has some deeper discussions that we can't go into here. But any questions as well?
So Scott White from Google. So with respect to FBAR, how is it talking BGP? How does it check what the BGP configuration is, and how does it gather other stats off the switches themselves?
OK, so FBAR is built to react to alarms. So we'll actually have an external system that is that we basically configure with different metrics. For example, S&P polling or whatnot.
What I mean to say is, OK, yeah. So S&P polling is how you get the stats, and how do you actually like reconfigure the BGP? Is it just CLI? OK, so yeah, so it's two parts. It's getting the stats originally. So if you take the whole workflow of the actual session, the issue there,
we generate an alarm based on the actual syslog message initially of the fact that the BGP session went down. But the rest of the actual interactions to the device are basically scripting around CLI commands. So literally FBAR will actually launch an SSH session to the box, and it'll be programmed in the remediation script that the network team would have written of basically a step-by-step of what commands to issue, what to look for, and what to kind of perform on that. The remediation script itself is actually Python code, so it's not like this. It's not literally send and check like an expect behavior, but it's Python code that kind of walks around simple expect CLI kind of commands.
Oh, there we go. In the center.
Hi, Leslie Carr with Wikimedia.
Cool.
Are any of these tools open source and available to the NANOG community?
So the FBAR one is actually publicly talked about. I don't believe it's open source right now. Some of these, in a way, are. So for example, we built the backend system Aggiornamento based on Thrift. The idea of Thrift is an open source project now with the Apache Foundation. That's kind of veers off a little bit and digresses, but the idea of Thrift is open source. But I don't think any of the other systems are just yet, mostly because we've been moving kind of quickly and haven't quite stepped back and spent the time to do that.
Left, back. Sorry, you were right.
Jared Manzer from GoDaddy. Regarding the Python environment, did you use a programming framework, and did you consider using things like an AMQP service-oriented architecture, something like RabbitMQ?
So in terms of the Python framework, we do most of our so in terms of all the Python framework, we do most of our actual coding directly in Vim, so just normal text editing. But there's a lot of tools built around Facebook infrastructure to let us kind of build on each other. So for example, I mentioned we integrate with things like the task system to help notify people, and also the idea of finding out who owns the servers. There's a lot of tools that other teams have built within infrastructure that kind of let us expose and access that information more generically so that we don't have to directly access different databases, but we can kind of go through intermediary helper services. The other question on the frameworks, I kind of forgot the other question, but I wasn't familiar with what you were asking on the other part, if that helps.
You can come back and ask again.
Cool.
Same, back left, back right.
Paul Porter with Topsy. In regards to, as you're describing, having automation to the point where if an alert fires, there's a script that can take a look under the hood, determine if something's wrong, and then possibly just discard the alert if possible. So we're doing a lot with automation as well, but where do you draw the line? Typically, if you're getting alerts, a lot of them which are being discarded, there's either something wrong with your check or something wrong with the device, or something is wrong. Generally, there's not alerts that fire off that you can just ignore. So do you now have people that are going through checking what's being discarded, or do you find yourself losing any visibility to an impending problem because a lot of I guess as the saying goes, where there's smoke, there's fire?
Yeah. So that's a good point. We basically still eventually go back and look at kind of overall what is being thrown away to kind of make sure. One thing to note, though, is we don't filter every single alert with FBAR. So for example, if it's a critical backbone device connecting, for example, links that cross-connect between data centers, there's some intelligence built in that says, hey, regardless of what this alert is, it's super important because it might be a ton of capacity that might have been affected. We basically use FBAR more to kind of help us weed out the smaller things. So for example, if a rack switch generates an alarm, because we actually monitored even the syslog at every rack switch, well, sometimes with rack switches, you'll run into problems that are probably a problem, but you can ignore. But since we monitor all syslog messages, it's interesting in that there is likely some cleanup we could do and not generate an alert to start with. But we kind of go for the idea of trying to generate too many alarms and then pare it down versus losing them. Because we used to not alert on anything, and now we've taken this opposite approach, which Peter here is laughing about, which actually, would you like to help on this one? Yeah. This is Peter Hughes, by the way, with NetEng as well.
Yeah, so I think to answer your question, when we get a bunch of alerts that we don't have classified or maybe we're classified as drops, we also have graphs that we look at to see if there's a spike in any given type or any given time. So we can see like, okay, there's 10 alarms right now, but there were 3,000 that were ignored. So that in and of itself is like considered a problem.
Thank you.
Rear left, or center left, sorry.
Wayne Bouchard, Limelight Networks. One question I had was the upgraded systems that you talked about with regards to updating configurations, firmware, what have you. Is that confined simply to the edge devices, that is those that are close to your clusters, that also incorporated into the, more important, the higher scale backbone interpop connections? And also, with regards to that, how do you address the introduction of new gear, new equipment, new technologies into your network with this upgrade facility in place? Surely that must create a few problems.
Yeah, so the first question, in terms of whether or not, because I talked deeply about the rack switch, I mentioned that more specifically because the rack switch was our biggest problem area, because we just simply had way more devices there. And they were always ignored the most, because the backbone, while really important, we had a lot less devices, so that wasn't as painful. Today, we do not do the backbone or cluster switches with that system, mostly because it's relatively new and we're still baking it. But there is work in progress to add backbone upgrade support and also add the cluster switch support. And then to your other question, in terms of introducing new devices, we're very big on being multi-vendor for everything. So today we have multiple vendors. And so when we go to build anything, we don't try to constrain ourselves to any single product or any single CLI. So for example, if we're writing code that's going to log into a device, we generally will, even if we only have one vendor deployed, but we have other vendors in use of other parts of the network, we'll write the software to actually handle all like 3 or 4 or whatever vendors we might have in that case. I think the focus from the beginning when we write tooling like that to already support other vendors is kind of what saves us the heartache of later adding one. But there are occasions where we'll add another vendor that is totally new. It causes some problems at first, but it's just more software to write, and it's not too unmanageable at that point, though.
We got time for one more question. Anyone? Okay. Well, thank you very much.
Thank you for coming. Cool.